Section 11.3, the integral test and the estimates of sums. So we're going to learn new tests. We learned divergence test, we learned integral test, we learned telescoping sum stuff. So here we learn the integral test. Just so you know, later on by the end of the chapter, when they give you a random series, ask you to test if it converges or diverges, one thing to keep in mind that the integral test would be the last one to use, because there's many requirements and more work to do other than other tests. So what is the integral test? So let's say if sum of an is a series with positive terms. So if you list the terms out, they are positive terms. We let an be represented by a function f of x or f of n. So be a function, so let an f of n be a function in n. If three conditions, if f is 1, decreasing, must be decreasing, and continuous on an interval, let's say a to b, then both the series an from n equals 1 to infinity and the integral from 1 to infinity f of x dx, they both converge or diverge. So what does that mean? It means you transform the series into an integral, a function, and get an integral, and you integrate this as we did in the previous chapters. If the integral converges, then the series converges. If the integral diverges, the series diverges. Okay? Let's look at an example. How about if we need to test if this series converges or diverges? We know it diverges, right? It's a harmonic series test. We know it diverges. But we're going to see how to use the integral test to check this converges or diverges. First, in order for us to use the integral test, we have to check two conditions, continuity and it's decreasing. So first, you remember how we said f of n equals a sub n equals f of n? We write f of x equals 1 over x. So remember, this function, the graph of it goes like this, but we're only working from 1 to infinity, so we're working over this. So which is continuous, you must state that down, over the interval 1 to infinity, because that's where the limit is. And we need to check if it's decreasing by finding the derivative for this. I'm sure everyone knows how to find that derivative. So notice this is less than 0 over the interval 1 to infinity. So it's decreasing. So decreasing and continuous. So the integral test is applicable in this case. So what does the integral test say? I have to find the integral from 1 to infinity of that function dx. And how do we do this? If you remember, this is an improper integral from 1 to a, 1 over x dx. Then limit as a goes to infinity. This is natural log of the opposite value of x from 1 to a. But we know it's x going to be positive here. So limit as a goes to infinity, natural log of a minus natural log of 1. Natural log of 1 is 0, and this goes to infinity. So this tells us it diverges. This means the given series diverges as well by the integral test. So a lot of students don't like this test because there's a lot of work involved, including checking continuity, checking it's decreasing, and then if these two conditions are met, then you have to do the integral as well, which is a lot of work. So we know, as another example, we know like 1 over n squared. know that converges. If you try to do the integral test, it will show you it converges by the integral test. But let's look at another example. Let's say n squared over 1 plus n cubed from n equals 1 to infinity. So again, use the integral test to check if this series converges or diverges. So first thing, it's important to start saying an can be represented as f of n, which I'm going to do f of x here. It's easier. We say the function of x, which is x squared over 1 plus x cubed, is continuous over the interval 1 to infinity. You must state that out. We can't just say it's decreasing unless we test it out. So we find the derivative using quotient rule. The bottom one times the derivative to the top minus the top times the derivative to the bottom one. And when you simplify all of this, what are you going to get? We get x times 2 minus 3x cubed divided by 1 plus x cubed all square. So the first thing you note, denominator is positive. So how do I know if the top is positive or negative? Well, x means from 1 to infinity, so that's positive. How do I know about this? Is that positive or negative? Well, if you happen to solve this equal to 0, you're going to get this equals 2, x cubed is 2/3, hence x is the cubic root of 2/3. So it's going to go like this. We know it's going to go from 1 to some other place, right? But what is that value located? Is it before 1 or after 1? So 0 is here. Is that above 1 or below 1? Doesn't matter. What matters to me is if I put that on the number line, after this value, when I pick any value I pick after this, is that going to be positive or negative? Let's say you choose 1. You choose 1 here. What are you going to get? 2 minus 3, negative. If you choose x equals 2, what are you going to get? 2 minus 3 times 8. So that would be negative. And notice, as you increase the x value, this value, the value of x cubed, will increase really fast. So that will keep that part always 0 for all x. That proves it's decreasing. Since that's decreasing, okay, and the function is continuous, that tells us that we can apply the integral test. We can apply the integral test. And the integral test says you go from 1 to infinity x squared over 1 plus x cubed dx, which you can rewrite as limit a goes to infinity 1 to a x squared over 1 plus x cubed dx. You can do the integral on the side with no bounds first. This integral can be found using u sub 3x squared dx. So 3 here, 1/3 out. So 1/3 du over u. 1/3 natural log of opposite value of u. 1/3 natural log of 1 plus x cubed. So then we have the limit as a goes to infinity of the answer I just found for that integral from 1 to a. Substitute a in, you get 1/3 natural log of 1 plus a cubed. You don't need the absolute value, minus 1/3 natural log of 2. If you pass infinity in here, that will go to infinity, so it diverges. Since this one diverges, then we say the given series, which is n squared over 1 plus n cubed, also diverges, and you must specify which test was used by the integral test. So that was about the integral test. You can practice more problems later on. We have another test to introduce called the p-test. So the p-test came from what we call the p-series. So the p-series is written in the form 1 over n to the p. So we call the p-series because we raise that n to the pth power. So this series converges depending on the value of p. Converges if p is bigger than 1. And diverges if p is less than or equal to 1. P is less than or equal to 1. That's the easiest test to work with. So if we ask you tests for convergence, divergence, remember this 1 over n, we did that earlier. What is p here, the p value? P is 1. So it should be divergence. This one diverges by the p-test. We did use integral test earlier, which took some more work to do by checking continuity, find the derivative, make sure it's decreasing, and then we did the integral. There was a lot of work. But here you can tell right away, this kind of series is called harmonic series, this one. But if I change this to 1 over n to the third, then what is the p-value here? It's 3. So then it converges. As long as the p is bigger than 1, converges by, again, the p-test or p-series test. How about something like k times the 4th root of k? Check if it converges or diverges. So this one goes as the sum of 1 over k times k to the 1/4, which is 1 over k to the 5/4. And now I can tell what p is. P is 5 over 4, bigger than 1. Converges by the p-series test or p-test. How about if we change it to 5 over k to the pi and try another one, maybe like k to the third over or k squared of 3. So for the first one, even though there's 5 in there, the 5 doesn't affect the integral. You can pull it outside. The 5 is not going to make the integral converge or diverges. So from here I can tell what p is. The p value is pi, which is more than 1, so converges by the p-series test. For the other one, I don't know what p is, so I have to do some rewriting. So maybe do the bottom minus the top minus the bottom based on the exponent properties. So here the p-value is 2 minus square root of 3. Square root of 3 is less than 2, right? It's like 1.7 maybe. So this is positive. So bigger than 0, but is it bigger than 1 or less than 1? Less than or equal to 1. Is it bigger than 1? Less than 1, right? So if that's about 1.7 and 2, so that's less than 1. If it's less than or equal to 1, then it diverges. Diverges by the p-test. We did something here. Notice, let me go back to this. The p-test has to take this form. 1 over n to, so the n has to be in the bottom. So this has, we need to rewrite this as 1 over k and bring everything down, so it becomes root 3 minus 2. So it's like that. That's still less than 1. Diverges, just to be careful. Now, what happens is, notice how we said continuous and decreasing for the integral test. Make sure to also state that's positive. So 3 things. Make sure in the integral test, state it's positive, decreasing, and continuous. Those are the three conditions in order for the integral test to be applicable. That's the first note. Another note, some of the sequences, let's say I have this series, right, like 1 over n. So watch what happens. When we say n goes from 1 to infinity, that means if I choose n1, I got 1 over 1, 1. So it's like a point. If you choose n2, you got 1/2. You choose n3, you get 1/3. And this keeps going on and on. So if you plot those on the graph here, 1, 1 here, let's say, 2, 1/2, 3, 1/3, like that, right? So the series would go like this if you draw it, right? Now, in some cases, when you are drawing, if you plot a series on the graph, sometimes the series goes this way. It goes 1 here, another point here, another point there, another here, and then it starts going down this way. So it's increasing, but then eventually it's going to go down. It's going to decrease. So this is called eventually decreasing. So this is eventually decreasing series. So that's an actual mathematical term we use. It could be eventually increasing or eventually decreasing. So in this case, we don't worry about this part here. So this would be like a so tiny part of a huge thing. So we ignore it. We deal with it when we say eventually decreasing, the same as if it's decreasing. So that's why we don't care about it. Now, we can make the problem or give you an example a little bit more challenging than the other ones. How about find the value or values, find the values of P, okay, of P for which the series is convergent. And what's the series? This is the series, the sum of natural log of n over n to the p, n goes from 1 to infinity. I would like to test to see what happens as n goes to infinity. So I'm not going to know because I don't know what the p-value is. One thing I would know is if p is 0, just I start like looking at this and say, okay, in my mind, on the scratch, what if p is 0, that means the denominator is 1, right? 1. So what happens to ln as n goes to infinity? So what is this as n goes to infinity and p is 0? It's infinity, right? It's infinity. Make sense? So how about if p is positive, like more than 0? So let's say 1, right? So on the side, if you test p1 or 2 or 3 or whatever, so the limit of this is going to be what? Infinity or infinity. And then we can use L'Hopital. That will make it what? Oh, it might converge, right? If you do 2, maybe it might converge, 3 might converge. Okay, so now how about if so for p equals 0, I'm set, it diverges. I know it's going to diverge. How about if p less than 0? What happens? So imagine you have ln of n over n to the negative 1. What happens? This one you have to rewrite it as n times ln of n. And believe me, with L'Hopital's rule, this is going to diverge all the time. So when n is less than, or when p is less than or equal to 0, the limit of ln of n over n to the p as n goes to infinity goes to, this one goes to infinity. So diverges. So this one diverges for p less than or equal to 0. So now I want to worry about what happened after that. So if p bigger than 0, let's see what happens. Okay, let's see what happens. Here I can transform an into f of n, which I'm going to use f of x. So my f of x is going to be ln of x over x to the p. Keep in mind that p is positive. Now, this function, if you plug in x1, 2, 3, 4, you will always get from 0 on, like it's going to be eventually positive. So this thing is positive and continuous on the interval 1 to infinity. 1 to infinity. Then the other thing we have to do is find the derivative, right? We have to find the derivative for this function, which is we take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator square. And to simplify this such a fraction, what are we going to do? So we are going to multiply top and bottom by x to the p minus px to the p value and ln of x over x times x to the 2p. You can factor x to the p on the top, and I'll leave 1 minus p ln of x divided by x times x. So x to the p times x to the p, these cancel out. So you get 1 minus p ln of x over x to the p plus 1. Remember, p is positive. So what happened here? Well, the denominator is positive. So let's see, when is this, I want to know when is this negative, right? Like, is it negative, or, and if it is, when is it going to be negative? To know when is that negative, I'm going to do this. When is this less than 0? Right? And then we can solve for x. How do you solve for x? You subtract 1 on both sides. You divide both sides by negative p, so that will swap the inequality sign. And then x would be bigger than e to the 1 over p. So we say that this function, so it is eventually decreasing on the interval that I just told you about, 1 over e to the 1 over p comma infinity. So it's continuous, positive, and eventually decreasing. So we can use the integral test. All this works just to test if we can use the integral test or not. Now we say the integral test is applicable. The integral test is applicable. So how do we integrate this? We're going to find the integral from 1 to infinity of natural log of n, or x, over x to the p dx. And let me assure you that this is not easy to integrate, but what can we do here? Maybe we can do integration by parts? What do you guys think? Yes. Okay. We can probably do integration by parts. On the side here, x to the p dx, we have the LIATE trick. We have natural logs or logs first, so maybe we can take u equals this. Du is 1 over x dx, and dv is whatever is left, dx over x to the p. So dv is x to the negative b dx. So v is negative 1 over b x to the negative b plus 1, I think. So uv minus the integral of v du. Let's see what happens. U is ln of x. V is the x to the negative p plus 1 over negative p plus 1 minus v again x to the negative p plus 1 over negative p plus 1. Du is 1 over x dx. Remember, p is a constant here. So keep this the same. Minus, pull the denominator down, out, and inside this one, it's basically x, negative p plus 1 minus 1. So it's x to the negative p. So it becomes negative p plus 1 over the same denominator. So then, for simplicity, I can factor x and make it 1 minus p. Factor 1 minus p as well. That leaves natural log of x only there, minus 1 over 1 minus p. And if you want to combine them, if you like, 1 minus p squared, then you got 1 minus p times ln of x minus 1. Then we're going to find the integral now, 1 to infinity of natural log of x over x to the p dx equals the limit as, let's say, a goes to infinity of the integral from 1 to a natural log of x over x to the p dx. And we can use the answer we just got, limit as a goes to infinity of x to the 1 minus p times 1 minus p times ln of x minus 1 divided by 1 minus p squared from 1 to a. So notice here the limit depends on this. This means from x equals 1 to x equals a. So the denominator is not related to the axis. You can pull it outside to make things easier for us. And here is going to be more of substitution. You plug the xa first to 1 minus p times 1 minus p natural log of a minus 1 minus substitute x1, ln of 1 is 0, and you're going to get 1 to that power is going to be 1 times the other 1 inside, or negative 1, so it becomes minus 1. Then we need to find the limit as a approaches infinity. So now this works only notice what is affecting the limit is the 1 minus p that you see there. If 1 minus p is less than 0, okay, why less than 0? Because if it's less than 0, then you can bring it down and then you do L'Hopital's and then it will work out. But if it's positive, then you're getting an infinity times another infinity inside that will make it indeterminate, and it's not going to be easy to integrate. So the only way to get this out and work it nicely and get a value only under the condition that is gonna exist when p minus 1 less than 0. Sorry, 1 minus p less than 0. So then you can say this is less than -1, so p is bigger than 1. So this means we can conclude here that ln of n over n to the p, n goes from 1 to infinity, converges when p is bigger than 1. Just for fun, so as you know, we have been dealing with 1 over n to the p power. So we have a mathematician is named Euler. What Euler was able to do, and remember back then during his time there was no calculus, nothing, no computers. So he found out that if p is 2, and he proved that this exactly equals pi squared over 6. Pi squared over 6. Which is very interesting result. We know it converges, right? It converges. So he proved that if you take n1, n2, n3, all the way to forever, you will get pi squared over 6. And this whole chapter, you know, like we have a mathematician, his name is Ramanujan. Different people pronounce it slightly different, but let's say Ramanujan. And there's a movie about him. This guy did mostly about series, although passed away at early age, but he really wrote so many things about series, sequences and series.